Hey everybody, welcome to your video on hash tables. Now, if you're brand new to hash tables, this is a little bit confusing, but I'm going to do my best to explain it in a simple way. When I was first learning this, I just had to tell my two brain cells to pay attention, and I just had to go through example after example to get it. So, hash tables are used in a lot of popular programming languages, and it's very similar to an array, but instead of just putting values into the array, we're actually going to have key value pairs. So, what in the heck is a key value pair? And by the way, if you're coming into this because you really want to understand the hashing aspect of this, we're going to talk about that in this video. So a key value pair, you can think of it as an association between two values. So it might be a person's name and a person's ID. So let's go with that. We'll say ID is associated with the person's name. And this is an example of a key value pair. More specifically, you might have the value 3 and the name Caleb Curry. So whereas before, you may have just put Caleb Curry inside of an array, one of the spots here might have the value Caleb Curry, and then you might have other people's names in here as well. You no longer are just going to worry about the value, you're also going to have to worry about the key. Whereas before, you would index these just using integers that go up. You would say this is index 0, this is index 1, and this is index 2. So like let's say we had some other names in here. We might have John Smith and subscriber. That's you. There's also John Cena, but you can't see him. So before we would grab these using these numbers, which is pretty much just the offset. So let's say this was a collection called users. We would originally just grab these elements using these integers, which is just the offset. So to grab subscriber here, you would say start at users, and we're going to go offset 2. So the computer knows where to find the data you're looking for because it goes to the users array, and then it goes 2 elements off to grab the piece of data you're looking for. So that is how a traditional array works. But when we introduce keys, so we're not just worrying about values now, we have key value pairs. Instead of passing in that 2, you're actually going to pass in this person's ID. So like let's say your ID was 618. Here is how you would grab this element. So no longer do we just have Caleb Curry, John Smith, and subscriber, but we actually have the ID as well. So 3 is Caleb Curry, and we'll go with 75 is John Smith, and subscriber is 618. So let's talk about the purpose of a hash table now that you understand a little bit of what it's trying to do. So here are the primary purposes of a hash table and its benefit. The first one I have here is lookup table. And what this means is you can use a hash table to look up data by some key. So you can look up this person's name by the key 3. You can look up this person's name by the key 75. So that is the concept of a lookup table. It's a common concept in computer science anytime you just need to look up some data. Another example of what a lookup table might be is, let's say you have some zip code. I'm in the US, so I'm not really sure how things work in you other countries out there, but just focus here for a minute. 1, 2, 3, 4, 5, that could be a zip code, and you might have a lookup table to see what city this is in. So you would have this is the key, and this might be associated with, I don't know, Bellevue or something. Yeah, I don't know how to spell. Anyways, that's another example of a lookup table. Anytime you use some value to get extra information. The other main benefit of a hash table is extremely fast inserts and retrievals. Similar to how retrieving data from a normal array is very quick, you just take an array name such as data. That'll start at the beginning of the array in memory, and then you pass in some offset such as 32. Well, the computer is able to just jump to the correct position thanks to that offset. Hash tables are a little bit magical because they are still very, very fast for retrieval and inserting data, but we don't necessarily have to know that offset because we're not using an offset like here. We're actually going to use some key such as 618, 3, or 75. Where in this example, this 32 is referring to where it is at in memory. This number here, the key, does not. So hopefully that's not too confusing. This here is a normal array, and this here is a hash table. This is an offset or an index. This is a key. This does not directly tell you what position it's at in memory. This, however, the offset or the index, does tell you where it's at in memory. So you might be wondering, if this doesn't say where it's at in memory, how is it that we can still have very fast inserts and retrievals similar to an array? Well, the actual location in memory can actually be calculated from this key here. So 618 in this case acts as an input to some calculation that determines where to store this inside of memory. So you want to visualize that. 618 goes through some processing, and this processing is used to determine the actual memory location. Whereas with a normal array, that index can just be used immediately to get the location. The keys for hash tables just have to go through one extra step to get that memory location. But it's still an extremely efficient process as it is constant time. So this is an O of 1 operation. It's a constant time operation. Now, it's not perfect, and there's some issues that might come up with hash tables that we're going to talk about. So we might not always get a constant time for inserts and retrievals. However, it is still extremely efficient. All right, so I think we're getting a little bit too cluttered here. So what I want to do is I want to clear some of this off and go through a little bit in more detail how this process, going from a key to a memory location to grab the data, such as Caleb Curry or John Smith or whatever, what is this process and how does it work? Because this is the magic, the secret sauce, the secret formula of hash tables. So if you can understand this process, then you will understand hash tables and set yourself apart from a lot of people who are only able to use hash tables because they're very easy to use, but don't understand any idea how they work. So if that's what you're interested in, then stay tuned because we're gonna get into that and hopefully increase your knowledge and understanding. All right, so let's say we want to use a hash table in our code. It doesn't really matter what programming language. You can look up the specific syntax for whatever language you're using, but it's probably going to look something like this. We're going to have some variable, and we'll just call it data, and we can initialize that. So we will just start it out as an empty hash table. The way you might add an element would look something like this. Data. Then you pass in a key here. So let's say we pass in the value 3, which was my user ID, and we assign it some value such as Caleb. So if you're in Python, the hash table data structure is known as a dictionary. You may also hear associative array for various programming languages. So those are both common names to describe hash tables. But in this situation, we are creating an empty hash table and we add one element with the key of 3. So if you went ahead and analyzed data to see what it looked like, or if you just printed it out, it's going to look like this. Curly braces to indicate the start of a hash table. And then we're going to have the key and then the value. Something like that. And I'm terrible at drawing these curly braces, but those are curly braces, and that's a 3. Now to get that data back out, you just do the same exact thing. So as an example, you could pass to a function, we'll just say data, and use the key 3. So that is how you would pass in the value Caleb. If you tested to see if these were equal, it would pass as true. That's all you need to know on how to actually use a hash table. So it's very, very simple to use one, but it's a little bit more complex behind the scenes. So now I want to understand that hashing aspect and how this is actually stored in memory. And I don't know 100% exactly how it's done for any particular language, but it's going to be something very similar to this for whatever language you're in. So we'll just go through a simple example, and let's say when we create a hash table in memory, it gives us an array of a certain size. So let's draw that over here. And this might have 6 spots right one after the other in memory. So this works behind the scenes just like any other array, where it's just one continuous area of memory and each element gets one spot in this area of memory. So this here, key 3 and the value Caleb might be stored, let's say right here. Now to use the hash table, the actual location in memory is irrelevant to us, but if you want to understand the hashing aspect, it's important to understand that this is going to be assigned some specific spot in an array. Now the actual way it decides which position to store this at is determined from hashing. So the way it goes from 3 to index 0, 1, 2, 3, 4, so this is index 4, the way it goes from here to here is done in the hashing algorithm. So there is some hash function that does a transformation on this key to get some position in memory. And it's got to be, in this situation, either index 0, 1, 2, 3, 4, or 5. So this hash function, the way this actually works depends on a lot of things. What type the key is, probably what language you're in, and probably a bunch of other things. So a simple example of how this hash function might work is actually taking the key and modulus it with the size of the array. So I'll explain that in a sec, but it's pretty much going to look like this. 3 modulus 6, which is the array size. So you can generalize it and think of it as key modulus size. And as a refresher, the modulus is going to give us any remainder. So any remainder when you do 3 divided by 6, well, there's actually going to be the entire thing left. So this would actually give us the value 3. And let's say that is the algorithm it uses to decide where to store the data. Then this is actually going to be stored right here. So 3 Caleb. So convenient in that we have the same key and the same position in the array, but let's go through a different example. Let's say we want to add another element in here. So we say data index 664, and this one is going to be John. Well, following the same exact algorithm, here's what's going to happen. We're going to have the key 664 modulus with 6. So if you were to do 664 modulus 6, well, 6 goes into 660 11 times, so there's going to be 4 left over. So this will give us the value 4. So key 664, John, is going to go at index 4. So that is the basic process for how we go from the key to the actual location. So there might be some variations in there, a lot of prime number examples I've seen online and other ways of doing this process, but ultimately you're going to get a number 0 up to the array size minus 1. In this situation, it's actually impossible to get 6 because if it went in evenly, there would be 0 remainder. So for example, if you passed in 66 modulus 6, well, this is going to give you 0, which is going to go here. If instead you did 65, it's going to go into 60 10 times, and you're going to have 5 left over, so you get 5. So there's no way to go out of the bounds of 0 to 5. So that is why a modulus is often used. Also keep in mind that we are using an integer for the key here, but you can also use strings. So there could be an association between someone's email and their name, or an association between the person's name and their address, or whatever you want it to be. As long as this data type is hashable, you are good. And most data types are hashable. The only kinds that are not are things that often change. So for example, a list or a dynamic array is probably not hashable, but any of the immutable data types should be good to use for a key here. So now let's keep going through this example, and I want to introduce a problem with hash tables and how this problem is solved. I'll give you one example of how it's solved, but there's lots of different ways of solving it. So let's say we go through an example where we want to add in another key here, and we're going to pass in 64. And this person's name is Helen. Well, if we were following that same algorithm, 64 modulus 6, that is going to return the number 4. So let's go ahead and add Helen to, what do we do? John is already here. So does it explode? Do we explode? Well, that's exactly what happens. If you have a conflict here, you legally become an explosion. So exploding is one way to fix this. There's also other ones that are probably more ideal. And one common way to do this is actually to use a linked list. So what's going to happen is this becomes a node that actually points to the next node, which is in this case going to be Helen. So 64 is Helen. So that's why all that linked list garbage is now useful, because it actually can be used in these other data structures. So if you weren't paying attention for the linked list videos, face your consequences. So that's one solution for this problem, but there are other ones out there. So for example, you might hit index 4 and there might be already something there, so you just go to index 5. So collision resolution is the word used to describe these different options of fixing these collisions. The linked list option I told you is called separate chaining. The one where you go from index 4 to index 5 is an example of linear probing. Don't like the word probe, it's weird. I could probably go into so much more detail for hash tables because they're very in-depth. For example, at what point is 6 elements irresponsible, and instead it would be better to have 600 elements or 6,000 or 60,000 or whatever, you know, because if we're just going to have 6 elements here and then a linked list of 20 quadrillion elements, then that defeats the whole purpose of hash tables, because if you think about it, to find this element, we're going to have to start at John and then go one node at a time searching through this linked list until we hit that data. So how that might work is if you try to access data index, what was it, 64? It's going to basically take this key, hash it, it's going to get the result of 4. It's going to realize that's John. We don't want John. John smells weird. So we're going to go down our linked list to, fortunately, Helen is right there. But imagine if we had a really super long linked list, we're going to negate the benefits of the hash table because now we are subject to the operation speed of a linked list, which, by the way, iterating through a linked list is an O of n operation. So that's gross. Now, it's not going to be O of n for the entire data structure here. It's just going to be O of n, where n is the size of the linked list. So if your linked list is 100 elements long, it could potentially take 100 operations of checking the node, going to the next node, going to the next node, and so forth. But anyways, I think I'm getting into the weeds. If you want to know more of that information, you can research that. So beyond the different ways to do collision resolution, you can look up how these data structures are dynamically resized and when that happens and what is the cost of doing that. There's all kinds of different things you can research with hash tables that I'm not going to get into in this video, but that's just because this is the intro data structures course. But hopefully we'll get into this stuff in more detail